Well, hey everybody, Mr. Reeves back with you, and in this video today we're going to be talking about the converse of the Pythagorean theorem. Alright, but before we talk about the converse of the Pythagorean theorem, let's do a little background. First of all, when you are talking about different types of triangles, one way you can describe different types of triangles is by their angle measurements. And when you do that, we talk about three different types of triangles: acute, obtuse, and right triangle. So an acute triangle is a triangle where all the angles are less than 90, or acute. An obtuse triangle is where one of the angles is more than 90, or obtuse, and the other two would be acute. And finally, a right triangle, the type of triangle that we are focusing on right now, is a triangle that has one right angle. So just real quick, I just wanted to quickly go over that with you, these three types of triangles, so you have a bigger picture of what we are talking about when we're talking about proving a triangle is a right triangle. Second thing I want to talk to you about is converses of statements. All right, so if a statement is a conditional statement, which conditional statements usually have the word if and then, all right, it is a statement like this: if it is raining, then there must be clouds. Notice it's called a conditional because the second thing depends on the first thing. We call this first part the hypothesis and the second part the conclusion. All right, so this statement says if it is raining, then there must be clouds. Now the converse of that statement switches it around, and it makes the hypothesis the conclusion and the conclusion the hypothesis. So instead of saying if it's raining, then there's clouds, we say if there are clouds, then it must be raining. All right, do you see how we switch those around? Now you'll notice the first statement is true. You cannot have rain without clouds. The second statement is false. You can have clouds without rain. So it's very important that you understand that when you have the converse of a true statement, it often will be false. However, in the case of the Pythagorean theorem, both the original conditional statement and the converse are true. So if a triangle is a right triangle with legs A, B, and hypotenuse C, then a squared plus b squared must equal c squared. That's the Pythagorean theorem that we have been using. Its converse says if a triangle, so you have a triangle that has the shorter sides A and B and longest sides C, and if it's true that a squared plus b squared equals c squared, then it's a right triangle. Okay, notice in the Pythagorean theorem, you're starting with it being a right triangle. That's your hypothesis. Your conclusion is a squared plus b squared equals c squared. In the converse, your hypothesis is a squared plus b squared equals c squared, and therefore we are concluding that the triangle must be a right triangle. So before, we were trying to find missing parts of a right triangle, or side lengths or distances. Now we're simply trying to prove, is it a right triangle? All right, and if you're wondering why would we care, because there's a lot of things you can do with right triangles that you can't do with other triangles. So we are in lesson A2 in the Accelerated Math 7 textbook, testing the converse of the Pythagorean theorem. Well, the lesson is called the converse of the Pythagorean theorem. So again, the Pythagorean theorem says if it's a right triangle, then a squared plus b squared equals c squared. The converse says if a squared plus b squared equals c squared, then it is a right triangle. So it's simply a matter of testing out that statement. All right. Now again, when you have three sides, the longest side, if you're testing this converse, will always be C. The other two are A and B interchangeable. I just want to say that because if you look at how they've listed them, they always list C last. But when you're testing three sides, pick the two smaller ones to be A and B, and they're interchangeable, and pick the longer one to be C. All right, so here we go. So here we're going to test it. We're going to go 3 squared plus 4 squared. And when we do 3 squared plus 4 squared, we get 25. All right, and if we do 5 squared, we also get 25. So is a squared plus b squared equal to c squared true? Well, the answer is Yes, you can see it right there. There's a squared plus b squared, and there's c squared. Makes a right triangle. Yes. Okay? All right, what about if we do the next one? 5 squared plus 12 squared. I want to do, whoops, it did not go back. Let's try this again. 5 squared plus 12 squared. When I do that, I get 169. And then when I try 13 squared, I get 169. So here, once again, we can see, all right, is it true? Yes, it is a right triangle. Yes, okay. All right, what about 7, 24, 25? 7 squared plus 24 squared equals 625. Take a wild guess what 25 squared is. It is also 625. So once again, we have yes and yes, and there it is right there. All right, well, I hope they get us to a no one soon so we could see what a no one looks like. All right, so we have 8 squared plus 15, whoops, let me go back. 8 squared plus, go back, there we go, 15 squared. Well, 8 squared plus 15 squared is 289. 17 squared is 289. And once again, the answer is yes. Let's try that last one. 20 squared plus 21 squared. We get 841. 29 squared, 841. So all of these are true, that a squared plus b squared equals c squared, so they were all right triangles. Of course, that's not always going to be the case. It's not always going to come out to be true. For example, if we take a look at 8, 10, and 12 on our calculator, if we go 8 squared plus 10 squared, well, the answer that we get is 164. But if we go 12 squared, we get 144, and 12 squared does not equal 8 squared plus 10 squared. So a squared plus b squared is not equal to c squared. Therefore, it is not a right triangle. By the way, someone asked in class, well, Mr. Reeves, can't I just do this? Can I put it in the square root like we were doing to find the missing lengths and go the square root of 8 squared plus 10 squared, and then check and see what I get? I get 12.8, which is not 12, and that is absolutely true. All right, so you can, if you want to, put it in the square root and then simply see if it matches up. So if we did this next one, again, if we started with the square root and we did 14 squared plus 23 squared, and if we take the square root and if we get 25, then it is a right triangle, but we didn't get 25. So the answer to this one would be no. If we do the next one, if we do the square root of 16 squared plus 30 squared, what do we get? We get 34, so that one did work. All right, so whether you just want to check a squared plus b squared and then compare it to c squared, or if you want to compare the square root of a squared plus b squared to c, you can do that as well. All right, so the rest of these are simply going to be applications of looking at if it is a right triangle or not. Remember, when you put two right triangles together, you do get a rectangle. So there is one problem on your assignment where they want to know if it forms a rectangle. Well, it would form a rectangle if it forms a right triangle. Any two right triangles together are going to make a rectangle. All right, so that is just a quick lesson on the converse of the Pythagorean theorem. Until next time, have a great day.